Yeah. Good evening, India, and good morning to the United States of America. On behalf of VIT Bhopal University, myself, Dr. Sharat Tripathi, I welcome you to this session on challenges of deep human flight missions, which is going to be given by Mr. George Salazar from NASA. VIT Bhopal is celebrating National Science Day 2024. In India, we celebrate this Science Day on 28th of February every year to commemorate the discovery of Raman effect by Sir C.V. Raman in 1928. At this juncture, it is very fine moment when we are going to have this session on the challenges of deep human flight missions, when yesterday our respected Prime Minister had unveiled the names of the astronauts which are going to be the part of first Indian mission, man mission in the space, that is Gaganyaan. So the Group Captain Prashant Balakrishnan Nair, Group Captain Ajit Krishnan, Group Captain Angad Pratap, and Wing Commander Shubhanshu Shukla will be the team of the first set of astronauts who are going to present India in the first Indian mission with the human to the space. We have planned a series of events in the Science Week celebration at VIT Bhopal. As a part of these events, in the lecture series, today we are going to have the first lecture by Mr. George Salazar on this topic of challenges of deep human flight missions. On behalf of VIT Bhopal, I welcome you, Mr. Salazar. So for his introduction, Mr. Salazar has over 40 years of experience in telemetry, communications, speech control, command and data handling, audio, displays and controls, intelligent lighting, project management and system engineering. He has been involved with the design of advanced telemetry, speech recognition, and intelligent computer systems, of which he has received various patents. He also led several advanced avionic technology concept investigations for the next generation space program. Mr. Salazar has received numerous awards, including the NASA Silver Achievement Medal, the John F. Kennedy Astronautics Awards, and the NASA Q. Johnson Space Center Engineering Directorate Legacy Award for his contribution to human spaceflight. He has also co-authored several technical papers on spacecraft design, system engineering, and human system integrations. He was assigned to Human Interface Branch in the Avionics System Division, serving as the Human-Computer Interface Technical Discipline Lead to develop advanced human interfaces. He served as the Displays and Controls Subsystem Manager for the Commercial Crew Program, responsible for the astronaut crew interfaces to the SpaceX Dragon crew vehicle, as well as the Artemis Human Lander System Computer Human Interface System Manager. Mr. Salazar has also served as the co-founder of the successful NASA JHC Human System Integration Employee Resource Group, with the key goal of infusing HSI into the NASA agency development process. Mr. Salazar received his Bachelor of Science in Electrical Engineering from the University of Houston and his Master of Science in System Engineering from Southern Methodist University. Mr. Salazar is a member of HKN, the International Honor Society of the Institute of Electrical and Electronics Engineering. He is a registered professional engineer in the state of Texas, and he holds an expert system engineering professional certification through the International Council on System Engineering. Also, he is a life senior member of the IEEE. Mr. Salazar recently retired from NASA after 40 years of experience and service to the space exploration. With the introduction, on behalf of VIT Bhopal, I welcome you again, Mr. George Salazar, to this session. It's over to you, sir. Please.
Thank you. Thank you for having me. Good evening over there. Good morning over here. I'm going to get ready to share my screen. And hopefully I go into presentation mode. All right. Can y'all see it? All right.
All fine. Please proceed.
All right, great. I'm going to start my presentation. And once again, thanks for having me speak to the VIT group. Very honored to share a little bit of knowledge about deep space flight. I know that many countries are starting to have the human spaceflight programs. I know India is pursuing that. And so it's a good opportunity to perhaps share a little bit about our deep space programs that we've been doing over the years. And so what I'm going to be talking about here is a brief history of human spaceflight. And one of the things that I want to point out is the complexity of human spaceflight has increased over the years. And then our planned human spaceflight programs, but there's challenges, and that's what I want to spend a little bit of time of. You see the back picture of Star Trek, and the reason I put that there is because, one day we're going to be exploring the universe with multicultures, people from, all over the world. And maybe one day we'll come across Mr. Spock from Vulcan. And so that'll become part of the exploration. But I know it's an exciting times, and it's there's so much to explore, so much challenges that we need international cooperation from different countries. So let me just talk briefly about human spaceflight, at least here in the United States, from the past and current standpoint. So, we started out with a Mercury program back in the early 1960s, and this was the very beginnings of human spaceflight. We didn't know if humans were going to be able to live and operate in space. And so the Mercury program was an opportunity to learn that. And it was just one little capsule, and the space capsule had about 55 switches on it. Most of the commanding came from the ground. The Mercury had no computer, so somewhat simplistic in design. And then fast forward a few years later, where we got into the Gemini program, where we had 2 astronauts, a little bit more complexity, and then we had a computer on board for the first time in a human spaceflight mission. The reason for that computer was because sometimes we would lose communications when the capsule was on the other side of the world. And if they were performing critical maneuvers and operations, the computer would take over and do a lot of the commanding for the astronauts. Then the Apollo space program, that's the one that took us to the moon. It was a incredible complex machine for back in the 60s and 70s. But it did the job, and it got us to the moon. We had 6 missions that we had astronauts land on the moon. We had a total of 12 astronauts that landed on the moon. But we didn't spend a whole lot of time there. We spent maybe a total of 3 days and 4 hours, something in that vicinity, as far as walking on the moon and working on the moon. So not much time has really been spent when we were doing the Apollo space program. But it did tell us, we could get there, but we also saw many challenges associated with just going to the moon. Space shuttle program, that's what I started with. Very complex vehicle. It launched like a rocket, orbited the Earth like a satellite, and returned to Earth like a high-speed aircraft. It had 5 computers on board to control the system. It had over 2,500 switches on there. It's extremely complex machine for 70s technology, but it was a workhorse. And of course, we shuttled a lot of credit for building the space station. The first space station was actually Skylab, and that was right after the Apollo program. We learned some of the fundamentals, if you will, of building a space station. And of course, now the space station that we have orbiting right now has been there for over 20 years. Extremely complex machine. It's about the size of a football field. It's got 300, somewhere in the vicinity of 360,000 sensors and over 100 computers for controlling this space station. Just to give you an idea, this is the kind of complexity we're going to be looking at for deep space missions for going to the moon, and more so going to Mars. And of course, the commercial crew program, which I've been involved with as well, both the Dragon system as well as the Boeing Starliner system. And it was the opportunity for commercial companies to participate in NASA programs. And of course, SpaceX developed the Dragon to launch humans to the International Space Station. And it was actually the return to sending astronauts from U.S. soil because the shuttle was retired back in 2011. So planned human spaceflight programs. Right now, what you're looking at here is somewhat of a phased approach to Mars. Ultimately, we will be going to Mars, but we need to learn how to live and work on another planet. And so what you see there is Earth, Moon, and Mars. And of course, Earth, we've been doing low Earth orbit operations with the International Space Station, as well as commercial partners. But going to the moon, you see a lot of activity going to the moon. The Orion spacecraft, space launch systems, commercial lunar lander, robotic surface missions, and of course, the orbiting gateway. That's the orbiting gateway is the station, let's call it the moon space station, if you will, that's going to be orbiting the moon. But this is the moon is going to be the proving ground. It's going to be a long-term operation to learn to live and operate on another planet and to basically check out the systems that are going to be ultimately used to go to Mars. Going to Mars is not going to be a simple task. And the other thing is it's going to be called Earth Independent Type Mission. The reason they call it that is because the communications to Mars from Earth is going to be in the vicinity at best 20 minutes. So in the case of an emergency, the astronauts cannot depend on the mission control centers on Earth to help them like they do right now on space station, as well as even going to the moon. The moon is not too far away, so they still will depend on the mission control to help them out. But once they go to Mars, it's going to have to be dependent on the spacecraft systems to help them out. So we're talking about artificial intelligence. We're talking about more intelligent machines, to help them let's say, operate and navigate these complex vehicles that are going to Mars with humans. And so we need to make sure we get that right. And that's why the moon program is called Artemis right now. Is going to be around for a long period of time. It's going to be a great opportunity for international partnership. We already have, I think, 14 countries that have signed agreement with the Artemis program to participate in there because there's so much that has to be done and develop and operate. So, I show pictures of a whole bunch of people on Earth. Basically, these are mission control centers throughout the different parts of the world that help operate the space station, and as well as when we go back to the moon. Well, we're not going to have those people when we go to Mars, at least for the time being, when we are on Mars. And so, again, as I mentioned, we're going to have artificial intelligence to help us out there. And we're going from a crew mission, robotic type mission control, robotic dependency to a more crew vehicle robotic dependency. It's going to be the crew, it's going to be the vehicle, and robots helping to explore another planet such as Mars. And so here's the Artemis program. And right now we're in phase 1, which is to the lunar surface. Actually, the date is actually changed from 2024 to 2027. But already we've done Artemis 1. We've launched successfully the Orion spacecraft, went to the moon, and did about something like 20 days of orbiting the moon, and then came back to Earth. We found that we had some deficiencies in the design, and that's the whole thing about testing. And they're currently working on improving those deficiencies. One of them is the heat shield. Uh, the next mission is going to be Artemis 2. These are going to be the first humans to orbit the moon. And it's right now scheduled for late this year. And it's going to be the first time that we have humans orbiting the moon, not landing on the moon, but orbiting the moon in a long period of time. Then, of course, we're going to incrementally start developing more capabilities. We're going to have a solar electric propulsion system that's going to be first going up into the lunar orbit. And then we're going to have the first pressurized moon module delivered to the gateway. This is the building blocks of the moon orbiting station. And they're going to have the human ladder system, and that was the one that I was working on. Basically, is going to be the taxi, for the lack of a better term, that's going to take humans from the orbiting moon gateway station down to the surface of the moon, and then back up to the gateway. There at the gateway, they can get out of the human ladder system, get inside the Orion spacecraft that's already docked with the gateway, and then return them back to Earth. Artemis 3 is going to be the crew mission to the to Gateway and to the lunar surface. Down there at the bottom, you see commercial lunar payload services. There's going to be a whole bunch of activity there in terms of providing, let's say, the infrastructure for living and working on another planet. One of the things that just happened recently in commercial lunar payload services was Intuitive Machines landed a system on the moon. Of course, they had some difficulties, but there's going to be other commercial partners and international partners. They're going to be participating in delivering robotic systems, habitat systems, and eventually we're going to have a we call living moon, a rather a livable moon base there on the moon surface, on the South Pole primarily. But there are challenges. There are challenges with all this, and it's and they're not trivial. One of the first things about space exploration is that humans were not designed for going into space. The gravities can be different, and that changes the physiological aspects of the human body. The body depends on the gravity, Earth's gravity, to build strong bones, build calcium. And so when it doesn't feel the gravity effects, there's bone loss. There's also muscular atrophy where the body basically grows. But then there's also things like balance disorders. Your balancing system in your ears and fluids and shifts and things of the sort, become altered. Space rate, of course, the way we get around a lot of that is to do on-orbit exercising. Space radiation, it's a big thing. It's a big thing right now, especially long term. And there's not only just the cancer risk, but what's called CNS, that's cognitive neurological system. Cancer can disrupt that cognitive neurological system and cause, let's call it operating, mental issues with the human. So protecting against radiation is going to be a big thing. And it's just not for the human, but electronics. And I'll mention that later in my presentation. Isolation and confinement, that's also a biggie in terms of health. In this case, is psychological health. We humans are social creatures. We want to be around people, or at least most of us do. And going into deep space, you're not going to have the luxury of being around a lot of people other than, the crew of 4 that are going with you to Moon or Mars. At least initially, until we start building a bigger infrastructure. But it's a big challenge, and we don't know still if humans are going to what are the effects of being far away from home in a planet that is far away like Mars. We do these what we call analog studies on the ground where people are locked away for about a year, but it's not really a good test. And the reason for that, and then of course we try to do the best we can. But one of the things, like one Russian scientist told me many years ago, he said that the test subjects that he had doing long-term long-term isolation studies is that the only reason they were able to put up with being in isolation for a long period of time was because they knew they were on Earth, and one day that door was going to open and they were going to get out. And that's not the case when you're on Mars. They're not on Earth, and there's no door to get out. So that's also a major challenge. And of course, psychological effects as well as physiological effects can influence the operation of systems. That's how people make a mistake. They're not feeling well, and they press the wrong button, they do the wrong execution command or things of that sort. So it's a major issue, and that's part of human-computer interface design that I was involved with, was trying to prevent human error. Of course, it's a hostile environment. There's no air, there's no food, that you can go out and look for. Your immune system gets compromised. And so we have to design systems, to protect them against that. And of course, being far away from Earth is things that can come up, like, for example, a medical emergency. Just recently on space station, they tested out a robotic operating system to operate on humans, and they did some very preliminary testing, and it's viable. But again, on low Earth orbit, it's not too bad for having a physician assisting, because it's only like a 1 second delay, to help people out. But when you're on Mars, it's 20 minutes. You can't afford to wait 20 minutes for a physician to say, okay, now cut here. It's going to be a challenge. It's going to be a challenge for developing, let's call it, intelligent medical systems. And there's also technology needs and challenges as well. Power is going to be a major issue, to power these large complex systems. Of course, you talk about solar power, and for the most part, that works like on the moon, where it's not too far away from the sun. But as you start going further away to go to Mars, your solar panels for generating electricity for a large complex system grows up dramatically. And so, you have to think about, well, are we going to use solar power, or are we going to use nuclear power? And that's an ongoing discussion right now. Of course, nuclear power, it would probably be the preferred approach, but there's still some trades having to be done there. Robotic systems are going to be obviously needed to help astronauts. Every time an astronaut goes outside of a spacecraft, it's a risk to the human. Meteorite could hit the astronaut, and those spacesuits only provide a certain amount of protection, and so they have to be cautious about going out into to the outside of a spaceship. But with robotic systems, they can control it from inside the vehicle, and perhaps prevent a catastrophic hazard to a human. But of course, we also have robots that do repair work, and that's going to be part of the robotic systems that are being developed, and robotics and autonomous systems for helping to build spacecrafts, or maintain spacecrafts, or habitats on another planet. Space radiation, there you see a picture of a computer card, and actually that's a radiation hardened computer card. Radiation can affect the electronics. Commercial products don't do very well in deep space. They're not designed for deep space radiation. The only reason we fly commercial parts on station is because Earth is protected by the Earth's magnetic field that basically blocks out a lot of high high energy particles that can destroy electronics. As we start getting further and further away from the magnetic field, where we have no longer protection, such as the moon and Mars, we have to make sure that these electronic components can operate for a long period of time on another planet. And of course, you've heard of Ingenuity, that was the little quadcopter on Mars that did something like, I can't remember, more than 25 flights. And it had commercial parts, and it's the news kind of misrepresented that Ingenuity quadcopter. It did have commercial parts, but some of the commercial parts were actually radiation testing, and there were a few things that were done to help protect against radiation effects. But it also had radiation hardened computer parts to basically serve as the command system, to oversee things going wrong with the computer chips. It could send commands to reboot, shut down, or do other things, to keep the system operating. So it's a challenge. It's going to be a challenge. And we're talking about artificial intelligence. It requires a lot of high computational power. But the problem with high computational power components that we have here on Earth don't do very well in deep space radiation. So that's a challenge in itself. The human and working with other people, you have the aspect of dealing with different cultures. You have different mindsets, if you will. And so, working in a group, call it group dynamics, is going to be a challenge, especially if you're away, for 3 years. And so the computer and human interface is also going to be important, where the human uses robotic systems and human computer interfaces, for command and control of the systems. And we still are learning about how to deal with cooperative human and robotic system operations. So that's also a challenge. There's a picture of a habitat, kind of a rendition of what they envision as far as a human habitat. That's going to be important too. Astronauts want a place where they can live and operate safely for a long period of time, and that habitat is going to be an important element, if you will. But it's going to be complicated. It's going to be complicated to protect it against meteorites as well as radiation, but then also provide nice, comfortable living quarters for the astronauts. And of course, space communications is going to be also a major challenge, if you will, just simply because of the delays associated with communications from different points. As we start evolving into space operations, we're going to have moon's communications. We're going to have Mars communications, Earth, Moon, Earth, Mars, Mars, Earth, Mars, Moon, and all this is not going to be simple in terms of communications. Right now, we have the Deep Space Network, but it's starting to, let's say, max out in terms of capability. And so we're going to have to be thinking about perhaps replacing it or modifying it to provide additional support for future space missions, especially human spaceflight missions. And Earth's re-entry vehicles. There you see a picture of the Mars Science Laboratory entry picture, and that was to it, for protecting the robot as it entered the Mars atmosphere. And that kind of re-entry systems only work for a certain amount of weight. The Mars Science Laboratory, as well as the Mars Perseverance, weighed about 2,000 pounds. I'm not sure what that is in kilograms, but that's the maximum that they can land a large vehicle on Mars. Well, these habitats and human spacecrafts are going to weigh way more than 2,000 pounds. So how do we land them safely on the Mars is something that we're challenged with. And of course, medical facilities designing MRI machines, X-ray machines that operate in deep space is also a challenge. In situ resource utilization, there's a picture rendition of a NASA ongoing development effort of in situ resource utilization. Basically, it's a machine, if you will, simplistically explaining this, is you put dirt in, and out comes water, and out comes fuel for the astronaut spacecrafts. That's simplistic, but that's basically what the whole purpose of in situ resource utilization is going to be all about. We cannot take all the water that's needed for a 3-year Mars mission. That's almost impossible to do. So we're going to have to learn how to live and operate off the land as much as possible to reduce weight, because launching weight gets expensive. And the more weight, the bigger the spacecraft, the bigger the complexity, and the more things that could go wrong. So, it's a trade-off, and that's part of systems engineering. So in in risk mitigation, the human robots for exploration are going to be interactive and mutually dependent. But there's hazards, and robots are the first. They're going to be the first ones to explore and get data to assess what risks are to humans, and that's why we send robots to the moon and to survey the moon. That's why we send robots to Mars to see what's out there that could hurt astronauts. Where's the best place to land them? Then the humans will visit the new worlds and conduct in-depth research. And so once we know where to land humans on Mars, for example, we know what we need to do there. But it's going to be expensive in terms of the challenges of the size of the crew. The robots are going to have to be part of the mission design. But we have to think about the hazards associated with the duration of the mission and the human workload. And of course, add that to the physiological and psychological health hazards of being in deep space. And robotic missions, we're going to have scouting ahead, to going to other planets, and we're doing that already. Assembly and repair, we're looking at that too. As I mentioned earlier, that's a technological challenge for doing that in a deep space environment. Refueling depots, that's something that we're looking at right now, and I think SpaceX is going to be developing the first refueling depot for its human lander system to go to the moon. It's a new concept, and we're hoping that this works out, because that'll make it easier to launch a lighter spacecraft, fuel it and then go into orbit, or Earth's orbit, where these depots are, refuel or fill up the spacecraft, if you will, with fuel, and then send it on its way to the moon and Mars. Mining and regolith collection, that's going to be a major challenge. Moon dust is very nasty stuff. It's very abrasive. It's got it's electroconductive or electrostatic conducted, and it just gets on everything. Back in the moon program, Apollo space program, Gene Cernan basically said that the biggest challenge of the moon was dealing with moon dust. So it's still going to be the same thing for the Artemis program. Human robot collaborative teaming, as I mentioned previously, is an area that we're doing research. In fact, we're at the Johnson Space Center where I worked. We had quite a bit of activity going on there. It's an area that we're going to have to be ready to make sure everything works properly when we go back to Mars, actually go back to Mars, and then of course telemedicine. And then reliable mission development method, basically design, build, and test. And so in the design phase, we want to make sure all features have been included. This is part of systems engineering, making sure that what we want and how we're going to build it have been done correctly. And we want to make sure it's built, designs and safety is built in. We test and build these systems and test and test and and test again, trying to weed out all the issues associated with what we call latent errors in the design. And of course, testing, not just testing of the systems, boxes, subsystems, but also testing with the human. Human in the loop testing is a major activity that we do in human spaceflight, making sure that the humans can operate safely these complex systems. Design for reliability and safety is very critical. Electronic components have a finite health life cycle, if you will, where it has a constant failure phase, and you can predict when it's going to fail. But there's on the low end, burn-in phase as well as a wear-out phase is where things can go wrong at a wrong time, and we always try to avoid designing for those particular phases, and that's why a lot of our missions have a finite mission envelope where we say, okay, after a certain amount of time, we're going to have to replace these components. So radiation effects can affect the hardware or affect that bathtub curve. Thermal effects, dust effects, electromagnetic interference effects can affect that what we call the bathtub curve. Software is a little bit different. Software doesn't have physical components that fail, but it does have errors. And what you see is that sawtooth that basically says, we have a lot of errors initially, but we weed out those, we find those errors in the software, and then the reliability goes up, or the failure rate goes down. But then if you introduce new software, you're going to have new errors, and then you basically get those errors out of the system. And this goes on until you stop upgrading the software, and you have a constant failure rate. And of course, for the human, there's the mistakes that human can make. It can be skill-based, which basically they know how to operate the system, but they forgot that particular day. And then there's the mistakes dealing with knowledge and rules, which basically says this person remembers how to operate this old system, but this new system, I don't quite understand how it operates, and they make mistakes. And that's something that we try to basically design out as we start doing human in the loop testing and seeing where those errors are in the system, and modify them to prevent human error later in the operation of a system. And of course, here's a simplistic Venn diagram for an optimized robot design. You got the human, you got the task, and you got the hardware in the system, and you're always trying to match the system to the human, and the human is trying to match, the task is being matched to the human. Certain tasks human can do well, certain tasks robots can do well, and that's part of the assessment process. Match the system to the task. We have to make sure that the task and the system are matched properly as well. So this whole thing goes on as part of the systems engineering process. One of the things I want to point out there at the top is you see the human, the hardware, the software, and the environment. And so these are the four major components of what we're always looking at when we're designing systems, because the hardware and software can work perfectly, but the human could make the system fail just simply because he or she did not understand how to operate the system. The environment is the other aspect that can affect the interaction of the human, the software, and the hardware. So from a standpoint of systems engineering, we're always looking at those four key elements as part of the design process. And then the mission safety prevention, this is adapted from James Reason back in 1990, where he determined that a error or a mistake that causes an accident is not attributed to just one thing, but rather potentially a series of things that happen that lined up properly. There you see what we call the Swiss cheese model. And of course, Swiss cheese has holes in it. And the holes in this diagram basically represent weaknesses in the barrier. And so these barriers are defenses against a failure. You try to design for the best, develop the best requirements, for the system, design the best system for the mission, do safety reviews to prevent any hazards, training to prevent any hazards, maintenance, obviously, to prevent any hazards. But the people that do this are human, and humans make mistakes. And those errors, or rather the holes, represent those mistakes. And there's a time period where maybe things, there's a hazard. Let's say they punch the wrong button or execute the wrong command, but maybe a design caught it, or maybe the safety caught it, and they fixed it. Maybe the training caught it, and they fixed it. But there's that one day where things just line up perfectly. All the holes line up perfectly, and a hazard goes through all the way through and causes an accident. I have a very strong belief in this philosophy, because if you read some of the accidents that happen in airlines and shipping and different areas of railroad industry, if you read it, you'll find out that there were multiple things that lined up that caused that accident or that tragic event. So I really like the pictorial explanation of how human error associated with all these things that can cause an accident. In conclusion, the path to the future missions, we're going to learn to live and work on other planets. There's no doubt about it. And obviously, other countries, India, even Africa, we got, oh my gosh, there's like 14 different ones right now. They're all going to be part of this learning to live and work in other worlds. And it's eventually going to help us settle in other worlds, going to Mars especially. That's going to be a major challenge. And so we need the expertise, we need the intelligence, we need the know-how and knowledge of other countries, to make this happen. And then from there, on to other worlds. So I think that concludes my presentation. I am going to stop sharing and return the meeting over to you guys over there.
Yeah, it was very informative talk by you, Mr. Salazar. And you have covered almost all the aspects of the deep human flight missions, starting from the conceptualizing, building the systems, testing them, and to the prevention. What we see in the space missions, you don't have options for the cure. But the one thing what you need to take care, that is the prevention itself. So I think that, and I hope my students as well as the viewers, they got good insight with your presentation. And this National Science Day celebration is catalyzed and supported by National Council of Science and Technology Communications, Department of Science and Technology, New Delhi, Government of India, and Madhya Pradesh Council of Science and Technology, Bhopal, Madhya Pradesh. So now I'm just opening this forum for the questions. I request my audience to come here one by one, and they can ask the question to Mr. Salazar. Participants, you can come.
Good morning, sir.
Good morning.
It's an honor for all of us to be able to interact with you today. And thank you so much for your presentation. It was very informative for all of us. So my question relates to, you have mentioned in your presentation about the adverse effects that humans will inevitably face in this due to the nature of the deep space manned missions of human physiology and human psychology. So can you highlight for us today a few of the key researches that are being done by NASA recently on space medicine and psychology? Thank you, sir.
Okay, the whole area, as I mentioned, physiological and psychological effects. We have a whole group at the Johnson Space Center, space medicine and human factors that are looking at possible solutions, if you will. We call them mitigation effects. There's something called human and health risk. I think we have something like 33 that have been identified. And each one of those, they're doing research in that area. Like, for example, the effects of radiation on the cognitive neurological system. And so there's there's actually kind of like two things going on. There's the part of the medicine, let's call it, drugs or medicines and things of that sort that'll help astronauts. But also we're looking at the physical systems and design of these physical systems. They're going to help astronauts, basically maintain their health for a long period of time. However, in addition to that, we're looking at the what ifs if these things affect their performance in operating systems. So it's a collective effort between the medical world, the psychology world, the engineering world, to make these systems as robust as we can.
Good morning, sir.
Good morning.
A very few number of spacecrafts have been able to make it past beyond our solar system. My question to you is, what technological advancements are needed to overcome the challenges of long distance space travel beyond our solar system, or even more so to other star systems?
That's a good question. Obviously, we have a couple of spacecrafts that have gone beyond our solar system. Voyager 1, Voyager 2. The whole thing has to do with propulsion, and so that's a big challenge. And if we can develop propulsion systems that can get us to a place very quickly, then the reduction in radiation exposure to the astronaut is reduced, as well as the let's call it the psychological effects of being in a spaceship for a long period of time. So some of the areas that we've been looking at in terms of increasing the power, if you will, or propulsion systems, for more speed is like, for example, the plasma rocket being developed by former astronaut Dr. Franklin Chang Diaz. It's called Vasimir. And so the plasma rocket basically could get us to Mars in about 30 days versus 9 months. Nuclear power, we're looking at nuclear power too as well. Of course, the challenge with nuclear power is dealing with the concern or the risk of the spaceship blowing up in our atmosphere and spewing radiation in the atmosphere. So there's some challenges there. And also there's challenges of protecting the astronauts with a nuclear power source going to another planet. So there's a lot of ongoing activity in terms of developing advanced propulsion systems, but it's not easy. It's not easy. If you think about kinetic energy, right? So you got something moving at a certain speed with a certain mass, you got a lot of kinetic energy associated with that system, right? And so if you're trying to, let's say, land a spacecraft on Mars, traveling at, let's say, 500,000 miles an hour, and it weighs something like 400,000 pounds, you can imagine how much kinetic energy is in that system going to Mars, and they got to bleed off that kinetic energy. It's not a trivial thing, not by a long shot. So how do we deal with that? How do we deal with something taking us to another planet very quickly, but at the same time having to deal with the kinetic energy aspects of something so big, traveling so fast, and trying to slow it down? So those are some of the challenges associated with deep space travel. But if we can reduce the time traveling to other worlds, other solar systems, I think that's going to be a major breakthrough in terms of space exploration, especially for human spaceflight. But of course, robotic missions will probably be the first ones to basically test out those kind of systems that are going to be developed.
Good morning, sir.
Good morning.
It's an honor to interact with you today. My question to you is that what strategies are considered to protect the astronauts from the radiation to protect the astronauts from the cosmic radiations of the planets we are traveling or the path we are traveling through.
Okay, so protecting the astronauts from the radiation, there's they're looking at different strategies. One of them is there's been talk about creating a wall of water. Water has a very good property in terms of protections against radiation, but there's also things like boron that's not very heavy, but protects against astronauts. Still, the whole thing about developing spacecrafts, as I mentioned in my presentation, is weight. You try to keep the weight down because the weight is going to cost you dollars to launch into space. So how do we deal with radiation effects and build something that that protects astronauts? And that's the challenge. I can tell you from radiation testing that I've done at a high energy proton test facility, they use big blocks of copper. These blocks probably weigh about maybe 8-10 pounds, and they're pretty big, but we can't carry a whole bunch of those into space to protect astronauts. It'd be very, very heavy. So we have to look at different ways. There's talk of using a way of creating a what we call artificial magnetic field around a spacecraft. Okay, very similar to Earth's magnetic field. Well, yeah, you can create a miniature magnetic field, but how much energy does that take to do that? And so you have to look at the pros and cons of each option, and that's part of systems engineering, is to do trade studies and seeing what are the pros and cons, if you will, of each option.
Good morning, sir.
Morning.
Sir, my doubt is regarding while the lander enters the atmosphere of another planet. Even in the Venus, the lander of any lander will not able to withstand its atmosphere. And if we are talking about deep space flight, there are various planets, and they have various diversity of atmosphere which we have to tackle. Even with the Chandrayaan-3, when the lander goes into the part where the sun doesn't shine, it get turned off. So how we are going to tackle this problem? It's been really problem since we have started exploring the space.
I'm sorry, can you repeat the question?
So my question is regarding entering another planet's atmosphere. It's very hard for a lander to tackle its atmosphere. Like even in Venus, our lander will not able to withstand even an hour to give us the data. Same thing happened with Chandrayaan-3 when the lander goes into the part of the moon where sun didn't shine. It went off. And similarly, as if we are going to talk about deep space flights, then of course there will be diversity of atmosphere that we have to tackle. So how are we really going to tackle that thing?
Okay, so in terms of communications, is your question trying to land something and communicating with that lander?
Yes, sir.
Okay, so yeah, it's a major problem. Going to the South Pole, there's already discussions about because of the visibility from Earth to that particular point, communications could be disrupted, and so that's the reason for we're looking at orbiting satellites. Right now, Like for example, space missions, we have TDRS for communicating from any point on Earth. So it's a major challenge going to Venus, and of course, this is the other thing is what kind of technology do we need based on where we're going to go? Venus has a very terrible atmosphere for communicating. So it depends on where we're going, and that's part of the mission design. You have to, and I showed you that picture of the four things: environment, human, hardware, and software. The environment, you have to look at the environment. What's my environment? So it's a major challenge. I can tell you that right now, one of the things that we're looking at is communications by laser, because laser communications provides high data rates, but there's still some challenges with that. But hopefully that works out very well. They're already doing some experimental stuff on space station right now on laser communications.
Good morning, sir.
Morning.
First of all, I'd like to thank you for a wonderful presentation. And my
Thank
question,
you.
my question to you would be on the current status of solar energy utilization in a spacecraft or in a space mission right now.
I'm sorry, can you repeat the question? There was a little bit of breakup there.
So my question to you would be on the current status of solar energy utilization in a spacecraft or in a space mission in general.
Okay, I'm picking up some static.
So my question to you would be on the current status of solar energy utilization in a spacecraft or in a space mission in general.
Okay, I picked up landing a spacecraft.
So the utilization of solar energy in a spacecraft or in a space mission.
Okay, I'm getting audio issues here. You broke up.
Yeah, am I audible? Is it okay? So he's asking about the solar energy utilization in the spacecrafts.
Solar energy in a spacecraft.
Yeah.
To use it?
So he wants that what kind of technology is being used currently and how much energy we are able to harness from the sun.
Oh, okay. How much energy from the solar sun? How much? Okay, so I mean, right now the technology is solar cells, and the space station has solar cells to generate about 100,000 watts of power. But the solar panels on space station are huge. They're they're almost the size of a football field. So it's very difficult to do that. Like for example, a deep space mission. And just one of the reasons for that is because if you got this big solar panel, there's a high likelihood it's going to get hit by micro meteorites or things of that sort. So it's solar energy can be good, but it depends on what you're going to be using it for. I can tell you that if you go deeper into space, solar energy doesn't work because you're getting further away from the sun. All right. And that's why Voyager 1, Voyager 2 used RTGs, radio thermoelectric generators, using plutonium for generating power. Because as you start getting away from the sun, it's 1/r², the amount of solar intensity. And so as you start getting further away from the sun, that means that your solar panels are going to get huge. And that's not the way to do it. That's not the way to do it. You have to look at different ways of powering your system.
Good morning, sir. Good morning, sir. My question is, after looking the cost, durability, and weight addition, does the self-filling material play important role today also? And what can be the alternative technologies in the near future?
I'm sorry, can you repeat the question?
Sir, my question is, after looking the cost, durability, and weight addition, does self-healing material play important role today also? And what can be the alternative technologies in the near future?
Okay, there's something going on. Can you repeat? I'm sorry. Well, I've got audio issues on my side.
Sir, my question is, after looking the cost, durability, and weight addition, does self-healing material play important role today also? And what can be the alternative technologies in near future?
Okay, what kind of technologies for what?
In near future.
I'm not catching the, what technologies?
Sir, in the near future, what are the alternative technologies? What can be the alternative technologies
All right,
for energy?
my apologies. Can,
She wanted to ask what kind of alternate energy sources may be utilized for the future missions.
okay, I am definitely having trouble. Can you, is there a way to type it in the chat?
Okay, we'll go for next question. I think there is some audio issues. Yeah. Anyone else?
Good morning, sir.
Morning.
So my question is related to self-healing materials. Is it really useful for space suits? And if yes, what is its role?
How hard is what?
So I'm asking, is self-healing material really useful for space suits?
Okay, I think I heard materials.
Self-healing materials really useful for space suits.
Oh, for the spacesuits?
Yes, sir. Self-healing material. Is it useful for space suits?
Okay, you want to know about the spacesuit design?
Sir, self-healing material. I'm asking, like the self-healing material, is it useful for space suits? Self-healing material.
Okay, I'm picking up spacesuits, but I'm not picking up the context of what do you want to ask about a spacesuit?
Sir, I'm asking.
We are just using the chat box. Huh? We'll ask few questions in chat.
I heard text, yeah. I am having difficulty now with audio, so apologies. Okay. Is self-healing materials really useful for spacesuits? The whole area of space healing, self-healing materials is going to be beneficial. And I'm not sure how you apply it for spacesuits, but obviously we're going to need something like that in case there's a hole punched in a spacesuit. So I think if we can come up with a scheme for self-healing material used in spacesuit, that would be really beneficial, even more so for a spacecraft. So that's something that we definitely could use some help on. Is how do you do that, and how do you do that reliably is going to be important.
So my question to you would be, so it's a different question related to a theoretical question related to time dilation, the concept of time dilation. So do you catch the term time dilation?
I'm sorry, you broke up. My apology.
So he had some questions on the relativity, the time dilation he was asking on the spacecrafts.
The what now of the spacecraft?
Yeah, the time dilation, time dilation.
Oh, time dilation?
Yeah, yeah.
Oh man, you're talking physics now. So time dilation. I guess it's going to depend on your and of course and if you're talking relatively here is how much time slows down on the spacecraft, and so we'll have to see how fast we can go to deal with the not only the time but also the mass of the object. If you look at Einstein's equation, the mass of an object increases as a function of speed. So as you get closer to the speed of light, the mass increases to infinity. So we don't know what that's going to look like. There's a lot of things in physics, that we still have to deal with.
Yeah, it was a great session. Now, at this juncture, at the end of this today's talk, I would like to invite the co-convener of this event at VIT Bhopal National Science Day celebration, Dr. Pradeep Kashyap, to present vote of thanks.
Thank you, sir. Good evening and good morning, Mr. George Salazar. The National Science Week is being celebrated at VIT Bhopal University. On this occasion, I would like to thank our Honorable Chancellor, Dr. G. Viswanathan, sir, Vice President, Mr. Shankar Viswanathan, sir, respected Assistant Vice President, Ms. Kadambari S. Viswanathan, ma'am, for their guidance and leadership, which is helping us in organizing such impactful events. I would like to thank today's speaker, George Salazar, Human-Computer Interface Technical Discipline Lead at NASA. In this Science Week, we will be having a lecture series where speakers hailing from all over the globe will speak in their line of expertise. I thank them for accepting our request to participate in this extended celebration week. In this continuation, I would like to extend my sincere thanks to VIT Bhopal administration, deans, directors, faculty, colleagues, students, and all the participants of National Science Week. I would like to thank Coordinator Dr. Sarachand Tripathi and Co-Coordinator Dr. Ashok Kumar Baral for their continuous support as the team member, members of the organizing committee. The National Science Week celebration at VIT Bhopal is catalyzed and supported by the National Council for Science and Technology Communication, Department of Science and Technology, DST New Delhi, and Madhya Pradesh Council for Science and Technology, MPCST. On behalf of VIT Bhopal, I thank NCSTC and MPCST for giving us the opportunity to celebrate for a week. Thank you.